So, um, imagine sitting down at your terminal right now, and you need to write a single piece of software. And this software needs to, I don't know, simultaneously translate a French novel, debug a massive legacy Python code base, and then generate a valid JSON payload for a REST API.
Right. Which, historically is a complete nightmare scenario.
Exactly. I mean, for decades of software engineering, accomplishing that meant you were writing bespoke logic. You were building entirely separate microservices, maintaining, distinct code bases for every single specific problem.
Yeah, completely different silos.
But today, that entire paradigm is just, it's collapsing into a single concept.
Hmm.
You don't write the logic anymore. You literally just ask for the output. So tonight, we're pulling from the capstone module of the LLM Mastery series. And the mission for you, the software engineer listening out there, is to really map the architecture of this shift. We are diving deep into the mechanics of foundation models.
It's really the absolute distillation of everything the field has been attempting to solve for, well, the last 10 years, I'd say. We've officially moved out of this era of artisanal, single-use machine learning models, right?
Yeah.
And we've entered the era of the universal reasoning engine.
One model to rule them all, as the notes literally phrase it. And to really grasp the architectural violence of this shift, we have to look at what we're leaving behind, right?
Yeah.
The deployment friction of the old paradigm.
Oh, the friction was massive.
Right. Like if you wanted a model to detect spam in a messaging app just, 3 years ago, you had to gather a massive data set of spam. You had to label it, design a specific neural network architecture, train it, validate it.
Deploy it, maintain it.
Exactly. And after all that compute and engineering time, if you ask that very same spam model to, say, summarize a news article,
it would completely fail. It would just crash or output garbage.
Totally fail. It only knew how to classify spam. So, okay, let's unpack this because it feels like the industry is moving from writing custom assembly language for every single piece of hardware to suddenly just, writing software for a universal operating system.
That's a really good analogy, yeah. The friction reduction is the defining characteristic here. In that old pipeline you just described, you were essentially forced to reinvent the wheel for every new feature.
Data collection, hyperparameter tuning, all of it.
Exactly. Every new feature in your application meant starting from scratch. Foundation models completely invert that workflow. You are no longer training task-specific models from the ground up. You take a massive, already pre-trained generalized model, and you just adapt it.
Okay, but let's pause and look at that from a systems design perspective, because I want to push back on this a little bit. In traditional software architecture, we preach the exact opposite, right? We build microservices specifically to avoid the whole monolith thing. Because isn't a jack of all trades usually a master of none? When you add infinite scope to a single monolith, you usually just get an infinitely slow, bloated, fragile system that nobody wants to maintain.
You do. In traditional software, yes.
So why doesn't a trillion-parameter neural network just collapse under its own compute weight? Why does throwing more generalized data at it actually make it, better at specific tasks?
Well, it's because we aren't hard-coding features into a monolith. We are expanding a continuous latent space.
Okay, explain that.
So in traditional software, adding a feature means adding explicit, rigid logic paths, right?
Yeah.
If this, then that.
Yeah, standard branching logic.
Exactly. And more paths mean more edge cases, more state to manage, more fragility. But neural networks don't operate on explicit logic paths. They operate on probability distributions and vector embeddings.
Right, that's all math.
It's all math. So when you scale up the parameters, the weights and biases of the network, and you feed it an unimaginably large data set, the model isn't storing bloated explicit instructions. It's actually building a denser, more highly dimensional mathematical representation of the data.
Oh, I see. So it's mapping the relationships between concepts rather than just storing the concepts themselves in a database.
Precisely. And this is exactly why it doesn't become a master of none. The massive scale allows the network to resolve incredibly fine-grained patterns. It starts to recognize that, say, the structural logic of a complex legal document actually shares mathematical similarities with the structural logic of a C++ program.
Wait, really?
Yes, because underneath, it's all just structured reasoning. And this shared representation is what allows for adaptation. You take this generalized representation and you just steer it.
Steer it how? Like with prompting?
Yeah, exactly. You either use prompting, so giving it instructions in its context window, or you use fine-tuning, where you slightly adjust the weights to heavily index on a specific behavior. Either way, you completely bypass the massive bottleneck of training the underlying intelligence.
Okay, but the mechanics of how that base intelligence is actually formed still requires a bit of a suspension of disbelief for me. Let's dig into the data side of things, because the fundamental training objective for these models is just next token prediction, right?
Right, predicting the next word.
It's basically just playing an incredibly complex game of autocomplete across, trillions of tokens of raw internet text, books, code repositories. So what does this all mean for the data? How does calculating the statistical probability of the next word translate to a model suddenly knowing how to architect a React component or, like, write a sonnet?
This gets to the core phenomenon of transfer learning at scale, and I'd argue it is the most important technical mechanism in modern AI right now.
Okay, lay it on me.
So what's fascinating here is that if a model was only trained on, say, a few million words, it could absolutely get by with shallow statistical memorization.
Like it just remembers peanut butter is usually followed by and jelly.
Exactly. It doesn't know what jelly is, it just knows the string of text. But when you scale the training data to trillions of tokens, memorization mathematically fails. There is simply too much variation, too much entropy in human language and code.
Right. You can't just memorize the internet because the internet is technically too big for its parameter count, so it's forced to, what, compress the information?
Yes, and compression requires understanding.
Wow. Okay.
To accurately predict the next token in a highly complex sequence, say, a nested function in a deeply abstracted Python script, the neural network cannot just guess based on the previous 5 words.
So it'll be wrong.
It will be wrong almost every time. So it is forced by the mathematics of the backpropagation algorithm to build internal abstractions of the concepts being processed. It literally has to learn scope, variable instantiation, logic flow.
So to win the autocomplete game on a code base, the model's internal layers are mathematically approximating an abstract syntax tree. Like, it isn't just mimicking syntax, it's actually structurally representing the dependency tree of the code.
Yes, that is exactly what's happening. It internalizes the underlying structure of the data it consumes.
That is wild.
It really is. When it reads physics papers, it builds representations of mathematical logic. When it reads narrative fiction, it maps out cause, effect, and human reasoning. And this is the transfer learning in action.
Okay, so how does that apply to a new problem?
Well, when you present this model with a novel, zero-shot problem, something explicitly absent from its training data, it doesn't just crash like a traditional program encountering an unhandled exception.
Right, the old if this then that fragility we talked about.
Exactly. Instead, it transfers the deep structural knowledge it gained across all those disparate domains and applies those generalized patterns to your specific problem.
It's almost like it's treating the new problem as a coordinate in that massive dimensional space it built, and just calculating the most probable path forward based on the physics of that space.
It's a reasoning engine, forged by the sheer difficulty of predicting the next token across every discipline known to humanity.
Okay, but then we arrive at this really fascinating architectural contradiction in the source material. Because here's where it gets really interesting.
Go for it.
If transfer learning at scale creates this ultimate universal reasoning engine, a true foundation model that can handle anything, why are we seeing specialized models popping up with specific names?
Right.
The notes heavily feature, BioGPT, Codalama, Bloomberg GPT. From an engineering standpoint, if the whole pitch is one model to rule them all, aren't we just going back to specialized models? This looks remarkably like a regression back to the old paradigm of bespoke, siloed models.
It definitely appears contradictory on the surface, but it's actually the application of transfer learning in its most potent form. We are absolutely not reverting to training from scratch.
Okay, so what's happening then?
To use another software analogy, think about taking a highly advanced general-purpose compiler. It understands all the fundamental laws of memory management, dependency resolution, execution logic, all of that.
Sure.
But if you want to deploy to a highly specific, resource-constrained piece of embedded hardware, you don't rewrite the compiler from scratch.
No, obviously not.
Right. You heavily optimize its heuristics for that specific architecture. You build a specialized skyscraper on a massive, generalized concrete foundation.
So you retain the global context, but you index heavily on the local syntax.
Exactly. That is the exact mechanism behind domain-specific foundation models. It is a two-step pattern. You have broad pre-training, followed by targeted domain adaptation.
Okay, so let's use Bloomberg GPT as an example.
Perfect case study. They didn't just feed a neural network financial spreadsheets and stock tickers,
No.
because if they did that, it would create a brittle model that only understands numbers but completely lacks reasoning.
It wouldn't know how to write an email or summarize a meeting.
Right. Instead, they took a model that had already read the internet, a model that already possessed that massive latent space of human logic, sentiment, and reasoning. And then they adapted it.
Through fine-tuning. And we
Yeah.
should probably clarify the mechanics of that because it's not just, appending data to a database. You are actually modifying the network, right?
You're updating the weights. And often the industry uses what's called parameter-efficient fine-tuning, or PEFT methods like LoRa.
Right. LoRa is everywhere right now.
It is, and for good reason. Instead of updating all hundreds of billions of parameters, which, by the way, requires a massive supercomputer, you freeze the base foundation model. And you only train a small, low-rank matrix of new weights that sits alongside the original layers.
It's computationally cheap.
Extremely cheap by comparison, but it drastically alters the model's output distribution.
That maps perfectly to patching a compiled binary. You aren't recompiling the entire operating system. You are just injecting a dynamic library that intercepts specific calls and routes them through a highly specialized logic path.
That's a great way to think about it.
So Bloomberg GPT keeps the universal reasoning engine like. It inherently understands when a news article contains negative human sentiment that might trigger a market sell-off. But the LoRa, the fine-tuning, heavily biases its vocabulary and formatting toward professional financial analysis.
Exactly. The domain adaptation steeps the generalized logic and specialized syntax. You get the robustness of the foundation model, but with the precision of a bespoke tool. And honestly, the realization that you can freeze the base model and efficiently patch it with adapters, that is what has caused an absolute explosion in the AI ecosystem.
Yeah, it has completely restructured the industry into a whole new supply chain.
It really has.
Let's actually map this supply chain because for anyone building software right now, understanding where you sit in this hierarchy basically dictates your entire engineering strategy. The source module breaks it down into 3 distinct tiers: the pre-trainers, the fine-tuners, and the application builders.
Which mirrors the traditional hardware to software stack almost perfectly.
Yes. At the very bottom, you have the pre-trainers. These are basically the silicon foundries of the AI world.
They are. They are the entities with the capital to assemble tens of thousands of GPUs and just run them continuously for months. Their only goal is to process those trillions of tokens and produce the raw, generalized foundation model.
And the barrier to entry there is astronomically high, right?
Yeah.
Restricted to just a handful of heavily funded organizations.
Yes, very few can play in that tier.
Then you move up a layer to the fine-tuners. In the traditional tech stack, these are your OS developers or kernel hackers. Like, they don't fabricate the chips, but they write the drivers to make the hardware usable.
Right.
In our ecosystem, these are the teams using methods like LoRa to shape the raw models. They align them for safety, they format them to follow instructions instead of just randomly predicting text, and they build the domain-specific models like CodeLlama or BioGPT.
They are curating the intelligence. They take the raw thermodynamic output of the pre-trainers and turn it into a directed, usable product.
Which leaves the top of the stack, the application builders. And honestly, you, the listener, are likely sitting right there in the application builder tier. In the traditional world, you don't need to know how to dope silicon to build a scalable iOS app.
No, you just use the SDK.
Exactly. And today, you don't need a 10,000 GPU cluster to integrate AI. You just need an API key to the foundation model. But I really want to zero in on the reality of what this means for the day-to-day software engineer, because we're undergoing a massive fundamental shift in how we build systems. We are trading deterministic code execution for probabilistic inference.
And that is a huge conceptual leap. It fundamentally breaks the traditional concept of unit testing, for one.
Oh, entirely.
Think about it. When you query a standard database, the schema is rigid. You know exactly what data types will return. But when you query a foundation model API, you are injecting a prompt into a probability matrix.
So the debugging nightmares are entirely new. You aren't tracking down a null pointer exception anymore. You're trying to figure out why an LLM suddenly hallucinated a library that doesn't even exist, just because the temperature parameter was set to 0.8 instead of 0.2.
Right, your database is now an API call governed by natural language instead of SQL.
It's wild.
It requires an entirely new discipline of engineering. But if we connect this to the bigger picture, This separation of concerns, letting the pre-trainers focus entirely on scaling compute, the fine-tuners focus on specialized alignment, and the app developers focus on prompt engineering and user experience.
This supply chain is what matures AI from a laboratory experiment into a true industrial utility. Standardizing that base layer allows the application layer to iterate at just warp speed.
True. But industrial utilities always come with industrial scale resource requirements. And the physical footprint of this new abstracted API layer is, well, it's honestly jarring when you look at the raw numbers in the module. We talk about the cloud and inference APIs as if they're these ethereal, weightless concepts.
They are very much physical. Right. The physical reality is that we are evaporating millions of liters of fresh water and burning gigawatt hours of electricity just to run these models. Wait, millions of liters of water for code.
Yeah.
This sounds incredibly inefficient and concerning from a sustainability standpoint.
It does. And the thermodynamics of the pre-training tier are severe. There's no way around it. When you cluster tens of thousands of high-performance GPUs, the heat density in those data centers is way beyond what traditional HVAC systems can handle.
So they have to use water.
Yes, they rely heavily on evaporative cooling systems. Add to that the baseline electricity required to power the chips themselves, and the environmental toll of coring that foundation layer is just a massive physical cost.
Just literally boiling a small lake to do matrix multiplication so a model can write a Python script for me. I mean, from a sustainability standpoint, taking that kind of hit to the power grid feels incredibly reckless.
It demands heavy scrutiny, absolutely. This raises an important question about net impact, though. You have to evaluate that cost against the counterfactual.
Okay, what do you mean?
Well, consider the trajectory we were on before foundation models emerged. We were heading toward a world of infinite bespoke models.
Ah, the era where every single feature required its own pipeline.
Exactly. Now imagine that scaled globally. Every hospital system, every financial institution, every tech startup simultaneously training and running their own specialized neural networks from scratch.
Oh, wow.
You would have hundreds of thousands of redundant data pipelines and distributed GPU clusters spinning up worldwide, all continuously training narrow models that cannot share their learnings with each other.
So the architectural efficiency of a foundation model might actually be its saving grace.
That very well might be.
By paying that massive, staggering thermodynamic cost up front to build one universal reasoning engine, you centralize the compute. You eliminate the need for those hundreds of thousands of redundant, decentralized training runs.
It is essentially the public transit argument applied to compute architecture. Building a massive, high-speed rail network requires a devastating amount of upfront resources, steel, and energy. But long-term, it is vastly more efficient than a system where every single citizen drives their own separate vehicle to the exact same destination. Centralized foundation models served via API represent a highly consolidated, efficient use of global compute, compared to the death by 1,000 cuts of decentralized, bespoke training.
That flips the perspective entirely for me. The sheer scale of the foundation model isn't just some party trick for better benchmark performance. It is the actual mechanism that prevents the global compute infrastructure from fragmenting into total inefficiency.
Exactly. The scale is the solution to the friction, both in software deployment and potentially in hardware utilization.
Which brings us full circle on this epic journey through the LLM mastery capstone. We have traced the architecture from the fundamental mechanism of next token prediction up through the latent spaces and transfer learning that forge these models into real reasoning engines. We've mapped the new three-tiered supply chain of pre-trainers, fine-tuners, and app builders, and we've weighed the physical thermodynamic reality of running probabilistic inference at a global scale.
It's a lot to take in.
It is. It is a complete paradigm shift in what it means to write software.
It really is the most rapid restructuring of the technology stack we have ever witnessed. But, I want to leave you and everyone listening with one final structural implication to consider before we wrap up.
Oh, all right. Let's hear it.
We just defined this mature, stable-looking supply chain. Hardware foundries, OS-level fine-tuners, and application builders writing prompts.
The new normal.
Right, the new normal. But consider the capabilities of the models themselves. Foundation models are currently achieving state-of-the-art results in writing Python, structuring datasets, evaluating logic, and even generating optimization scripts for neural networks.
Wait.
Yeah. Traditional software doesn't write itself. A traditional compiler cannot improve its own source code, but foundation models can output valid PyTorch training loops. They can generate highly synthetic, high-quality data. So the question becomes, if foundation models are the new universal operating system and they are getting better at coding and fine-tuning, how long until this perfectly stratified three-tier supply chain collapses in on itself?
Oh, wow. So if the model can evaluate its own outputs and write fine-tuning scripts, it can just act as its own OS-level developer.
Exactly. What happens when you provide a foundation model with a high-level architectural goal and it autonomously handles the domain adaptation, generates the API routing, and spins up the application layer entirely on its own? Will the foundation models of tomorrow act as their own fine-tuners and application builders? The foundation layer wouldn't just support the application layer, it would absorb it, cutting out the middle tiers entirely.
It bypasses the fine-tuners and the app developers completely. That is a terrifying and brilliant engineering problem to chew on. One model to rule them all, right up the entire stack. Well, we're going to leave it there for tonight. For everyone listening, thank you for joining this late-night exploration. Keep questioning the architectures you rely on, map your dependencies, and keep diving deep into the latent space. We will see you on the next deep dive.